Hello, welcome to this talk about the possibility of the delegated compositing on Ozone Wayland. My name is Maxim. I'm a browser engineer from Meghalaya who has been in this area for almost 9 years, about 5 of which I spent doing Ozone Wayland and X11 work. Today's talk is inspired by a very nice project I was part of called Lacrosse. If that name is unknown to you, Lacrosse was an effort to decouple Chrome from Chrome Ash so that the browser could have been updated independently from the Chrome OS devices, from the Chrome OS updates, allowing even outdated devices to have the up-to-date browser with bleeding edge technologies and features. So back to this talk, Lacrosse had a nice feature called Delegated Compositing, allowing Chrome to delegate compositing to the system compositor, involving less resources and having less overhead. Given the nature of the Wayland implementation, nothing actually blocks us from having the same feature on Linux as on Wayland again, except some missing protocols. Thus, this agenda for this talk is the following. What is the delegated compositing? What are the benefits? Then I will cover the current status of the feature, the missing bits, the big picture, how that is integrated within Chrome. We'll also talk about the Wayland protocols needed and cover which ones are missing from the major Wayland compositors such as Weston, Matter, and others. I also thought it would be nice to cover nuances the current implementation has due to some limitations coming from Chrome OS Wayland Compositor, and then talk ends with the summary. If you never heard, you would wonder what is delegated compositing. Is it rocket science? Well, not really. The concept is pretty basic. A client provides server with textures and the server performs compositing on behalf of the client. It is as simple as that. And if you still wonder how to visualize that, I have a slide for you. This slide shows how a client-side compositing works without delegated compositing. On the left side, you can find colorful rectangles right on the left top corner. So green, blue, yellow, and so on. Those are the textures that a client produced as a part of its frame. They can be some quads representing UI or accelerated canvas coming from render. Basically anything that is backed by DMA buffs. So once we have these textures rasterized, what Chromium does is that it draws those quads in a final texture. Well, assuming that we don't have here non-root render passes, right? Just for the simplicity, because it involves additional steps there, but the final idea is the same. And it does browser-side compositing, and that texture represents the final browser frame. So this big blue rectangle on the left bottom corner. Then the frame data is sent over to a system compositor, which does final compositing. It may also have frames from other clients, or it may need to draw some system UI. As you may notice, I have set compositing twice on the server and on the browser side. And here's where the trick comes. We can skip the browser side compositing, and just send our quads, these ones, uh, colorful, backed by daemon buffs, right to the system compositor, which can do exactly the same job for us, like on the right side. But there is a catch. Not all our textures, not all our quads are actually textures. We need to teach the compositor about our transforms. We also need to let the compositor know that Z order And also we want to work in the subpixel domain. And we'll talk uh, about that a little bit later. But why do we want delegated compositing as clients? The answer is simple. We don't know, it's just cool. Okay, that's a joke, and there is actually a nice benefit. And one may wonder, Chromium does already do a great job in compositing final frames in Viz. And by the way, Viz is the short for for visuals, which is the client library and service implementation for compositing and GPU presentation. So why would we ever need to do so? And the answer is simple. We want to reduce the compositing overhead and use less resources, which is especially handy in the embedded world. We also want to use less power and be efficient. As we have covered the high-level overview of what the delegated compositing is and its benefits, let's now talk about the current state. As was said before, the feature was designed for lacrosse, the purpose of which I explained in the beginning of this talk. And the feature allows to delegate quads only of root render passes, as delegation of the non-root render passes may present surprising glitches and more fine-tuning is needed. For example, issues with blending uh, while drawing render corners and so on. And to improve our chances of having less render passes, we made some changes to CC and this so that certain mask filters that involve, for example, rounded corners do not result in a non-root render passes. This was achieved by ensuring there are no overlapping rounded corners and other things. The architectural block of how we further pass the quads is Wayland subsurface. That's a special surface that allows a top-level surface to be constructed out of a few other subsurfaces, which perfectly works for our case. We also designed and implemented a few Wayland protocols that allowed us to pass additional information over the Wayland IPC to Wayland Compositor, as we are essentially needed to reconstruct a compositor frame metadata on the Wayland server side. These protocols can be found in third-party Wayland protocols folder and are implemented by Ozone Wayland and EXO, which is a Chrome OS Wayland compositor. So let's sum up how delegated compositing works. This is a high-level architecture overview. Here on the left, we can see compositor frames coming from different clients within Chromium, from browser compositor representing UI to renders and video frame syncs. Those clients send frames to Mojo, via Mojo to our Viz service, and it does service aggregation and forms render passes. It tries to optimize that in such a way that there is a root render pass that would allow us to do delegation. Then, skipping the draw step, we forward the quads to the GPU thread, then to the browser thread, serialize the data using Wayland means, and send the data further. It's worth mentioning that this is managed by a Wayland frame manager, which constructs a surface in such a way that each quads is represented by a Wayland subsurface. Should you need more details, don't hesitate to contact me by email. Now let's talk exactly about what Wayland protocols are utilized. There are a few standard things. Wayland subsurface, that is our overlay, and by the concept, quads are actually overlays, so don't be confused by that. Subsurfaces are owned by Wayland Surface. Wayland buffer, that's a DMA backed buffer that can be attached to any subsurface. Attaching the buffer multiple times to different subsurfaces is allowed. Uh, Wayland surface, well, nothing to add here. That represents a browser window. Of course, it has other roles like XDJ surface and XDJ top level. But these roles are for UI, not for the graphics handling itself. Also, the synchronization protocol. We needed a way to synchronize a client-side submitted GPU work and the compositor side compositing, as the textures we send may haven't been completed yet, by the GPU, even though the work was submitted. And that's a protocol we used. We also need to be sure that the return buffers are actually released and we can write them again. And now comes the most interesting part. One may think about uh, tons of protocols that would need that feature to work, but it's actually not. There is a surface augmenter which extends Wayland surface and also Wayland subsurface and adds ability to set metadata for rounded corners, clipping, and allow subpixel precision. Another interesting protocol is the single pixel buffer. It allows sending color buffers, and we used to have a separate protocol for that, but given that this protocol was added upstream, we switched to that one. Though we used to just clear DMA buffs with desired colors as a workaround before, which wasn't optimal. Let's return to the surface augmented protocol. That's the protocol that allows us to send additional data over the Wayland pipe and do things that Chromium does when it doesn't do delegation. We have here a couple of interesting roles, augmented surface and augmented subsurface. The first one extends Wayland surface to apply rounded corner clip mask and also enables us to work in the subpixel precision with its set destination size, of course. In contrast, WP viewport set destination works with integers, forcing us to round our destination while augmented surface set destination size works with fixed point numbers, providing us with 8 bits decimal precision. One may wonder why it's needed. The answer is the position of the quads. They'll be simply off their position and will look odd and have an offset artifact compared to non-delegated case. The augmented subsurface allows us to set position and subpixel precision and also set transforms. If you're interested, you can see the surface augmented protocol definition in the found in the third-party Wayland protocols. Uh, of course, the current implementation has some workarounds that are to be removed as non-Chrome OS-based Wayland compositors do not have this problem. But I still would like to mention that for the sake of clarity, in case of somebody experiments and finds the subsurface hierarchy odd. So EXA required Ozone Wayland to implement a workaround for construction of a tree of Wayland subsurfaces. What one would normally do is to place Wayland subsurface above and below any sibling surface or the parent surface. But it was impossible in the case of EXO due to the usage of aura. As a result, negative Z order relative to the root surface wasn't possible. And as a result, one had to create a subsurface that plays a role of a root surface and only then stack subsurfaces the way they want but not below the root Wayland surface. Luckily for us, that will be removed in the near future. And here is the visual representation of how it looked. On the left side, well, how it actually looks right now if you enable the Delegated compositing. On the left side corner, what one can see a root Wayland surface, which had all other subsurfaces attached to it. That surface didn't have any real buffers attached, but dummy one, so that Wayland is able to activate the top level surfaces and so on. And as I said, the subsurfaces are the ones that are stacked the way we want it, but not below the root surface. Once the code is cleaned up, the root surface will also have real buffers attached, and we won't have this awkward hierarchy. So let's summarize the status and the requirements. Chromium already has everything needed in CC and Viz, and there can be some optimizations required, like some elements cannot be delegated as they contribute to a non-root render pass, like scrolling in YouTube that resulted in some blurring masks. Ozone Wayland requires, of course, some cleanup to improve code maintainability, but it's not a blocker at all. But Wayland surface, they need support augmented surface and single pixel buffer. If I'm not mistaken, some of the Wayland compositors already implement that. Uh, yeah. Nevertheless, those are required for the subpixel position of quads and for the single color buffers. That way, the initial delegation support should work. However, more work may still be required to handle the edge cases. Thank you.